Okay, let's unpack this. We've got some really interesting material here today.
It's all about how a specific math concept, something you might even remember from college, can, well, unlock secrets in seemingly simple data.
Simple data, but really important data, right, from soil sensors.
Exactly, just moisture readings collected over time.
Yeah.
But the concept we're applying is integration, mathematical integration.
Right. And our mission for this deep dive is really to get a handle on how that process helps us see the bigger picture, like long-term soil patterns.
Precisely. Moving beyond just the single data points, it connects directly back to calculus, specifically differentiation and integration.
Yeah, I remember differentiation. That was about finding the rate of change, wasn't it? Like right now.
That's it. How fast is something changing at one specific moment? So for soil, how quickly is it getting wetter or drier, at this instant?
Okay, so the sensor gives you that snapshot.
The snapshot, yes. And differentiation tells you the slope, the rate at that exact point in time.
But just looking at those single moments or even a few snapshots, it doesn't always tell the whole story, does it?
Not necessarily. You don't always see the overall trend or the accumulation over time. It can be kind of misleading sometimes.
And that's where integration steps in, sort of pulls back the curtain, you could say.
That's a good way to put it. The sources we looked at really highlight this. Daily readings can jump all over the place. A bit of rain, some irrigation, evaporation.
Daily noise, basically.
Exactly, daily noise. But integration, well, it lets you sum up all those little changes or those instantaneous readings over a longer stretch.
Like over a week or a whole season.
Yeah, exactly. It's like seeing the whole movie plot instead of just one single frame.
Okay, so if differentiation is speed at one point, integration is like the total distance covered over time. Or here, the total change in moisture.
That's the core idea, the net accumulation or maybe depletion of moisture over that chosen period.
So what did the sources actually find when they applied this? Did anything, jump out from the data?
Oh, definitely. What was really interesting, according to the material, was how integration showed patterns they just weren't seeing with the daily checks.
Like what?
Well, for instance, there were times when the daily readings looked pretty stable, maybe even ticking up slightly.
Okay, seeming fine day to day.
Right. But when they integrated that data over, say, a week or two, it revealed a significant net loss of moisture overall.
Whoa, okay, so the day-to-day picture was actually hiding a bigger problem.
It seems so. It pointed towards other potential issues, things like maybe poor drainage, or perhaps plants were taking up way more water during certain growth phases than expected, things you just wouldn't catch from those instantaneous readings alone.
Ah, I see. So it helps smooth out that daily volatility
Mm.
and reveals the underlying trend, the system's dynamics. It's not just, is it wet today,
Mm.
but what's the overall balance sheet looking like?
That's a perfect analogy. The bank account one works well too, which the sources sort of hinted at.
Right, the daily deposits and withdrawals versus the monthly statement.
Exactly. Your balance bounces around daily. That's like the sensor snapshots or the rate of change.
Yeah.
But integration is like looking at your total spending or saving over the month.
The cumulative effect.
The cumulative effect that really tells you about your financial health, regardless of one good or bad day. This cumulative view for soil, the sources argue, is just as critical.
That really clarifies it. It makes the math feel less abstract, you know? It shows how integration shifts the data from just describing a moment.
To diagnosing a process.
Yes, diagnosing a process over time, turning numbers into, well, actual useful information about the soil's condition and history.
And thinking bigger, connecting this outwards. Applying integration like this isn't just about farming and irrigation, though it's obviously super important there.
What other connections stand out to you? What are the broader implications here?
Well, it really underscores how vital understanding these longer-term patterns is, and how mathematical tools like integration make that possible. It's fundamental stuff for, say, climate modeling,
Oh, interesting.
or understanding groundwater levels, or even in ecology, maybe tracking how nutrients build up or deplete in an ecosystem over time. Anywhere, you have these dynamic systems changing.
Right. So just to kind of recap our deep dive then, we've seen integration as this key mathematical tool. It lets us look past the immediate, sometimes noisy daily sensor readings
Mhm.
to uncover these really crucial long-term patterns, the cumulative changes. It gives a much deeper, richer understanding of what's happening in the soil.
Absolutely. Which kind of leaves us with a final thought, something for you, the listener, to chew on.
Go on.
Well, think about how critical it is to grasp these long-term trends, especially now, for adapting to big environmental shifts locally on farms or globally with climate change.
Right.
So the question is, what other fields, what other areas of life or science might be missing the forest for the trees? Focusing too much on the now, on those immediate snapshots, instead of integrating data over time to see the real story. What hidden narratives could math-like integration unlock elsewhere?